Hello everyone. How's everyone doing? This is Practical Compiler Design. Thank you all for coming, and let's get right into it. So, yeah, this is Practical Compiler Design. Just some information about me. I am a third year undergraduate student here at UTD, CS, and I'm doing a physics minor. Hoping for a PhD. I'll be applying to grad school next semester, likely the programming languages field. I've been studying compiler design since about fall 2021. I am working on a few compilers right now. There's one called Purple, which is just a fun little side project. That's what I started with. And then I submitted Pretty Bird to a programming languages conference to publish. I'll be hearing about that in about 2 or 3 weeks. I see familiar faces. A bunch of you probably know me from the computer security group. I was president for 2 semesters. I'm treasurer now. And so you'll probably be familiar with my lecturing style if you've been there. But let's get some information about the course. So one thing that I want to make very clear is that, excuse me, if you don't like programming, you're not going to like this course because that is the only thing we will be doing. The goal of the course is to walk out with a functioning, hand-built compiler that all of you wrote on your own, with guidance, of course. This course is not for credit. We are offering a certification from the CS department, but make no mistake, you're not getting any credit hours for this. I don't want to mislead anybody. And one thing I do want to specify is that, in my opinion, you don't need to know very much to participate in this class. When I started learning about compilers, basically everything I learned was on the fly. I didn't have any knowledge of abstract syntax trees or natural language processing. It was all completely new to me. And I think that's why I liked it so much, because it felt like this completely different frontier that I had never really explored before. And so I'm hoping that this can be that for y'all too. There are some things that you should know that'll make this a lot easier to get through the class. One thing that's very important is familiarity with assembly language. Doesn't really matter what kind of assembly language, but you should be able to read, and hopefully over this course you'll learn to write a kind of pseudo-assembly language that we'll talk about later. You should be familiar with trees and tree descent. That's pretty important. So just very basic recursive tree algorithms, depth first search, breadth first search, the very, very basic ones. There's not a whole lot. And then you need to be familiar with Git, because all of our submissions and our homework and our final project, it's going to be on GitHub or GitLab. You have to send me a Git repository link so that I can make sure you're not plagiarizing or anything like that. And all of these topics are covered in a review video I posted. This lecture is being streamed on YouTube. The link is in the Discord. And on that channel you'll find the review video where I go over basically all of the little basics that you need to know. So if you're feeling that you're not up to this after this lecture, maybe just go watch the prerequisites and see how little you really do need to know to get into it. So let's talk about passing the course. Like I said, the goal is to build a compiler by the end of the semester. And I don't have a whole lot of restrictions about this. There's a few that are important, but for the most part, I want to leave as much of it up to you as possible because, again, that's how I started. I was just doing this in my free time, and I really liked it that way. So first things first, you can write the compiler in any language you'd like. Something mainstream. Do not write it in oh man, what's a weird language? Don't write it in... Yeah, that one. The one that I've linked right here. I'm trying to think of the one that's named after the Ring of Hell. What is it? malbulge. Don't write it in malbulge. You'll get a 0. If you're unsure that your desired language is allowed, just talk to me, and we'll work something out. You have to compile an imperative programming language. Does anyone not know what that is? Okay, so C, C++, Java, Python, JavaScript, those are all imperative languages. The popular ones that everyone uses, because I'm not going to get into why everyone uses it, but the alternative is something like a functional programming language like OCaml or Lisp or Haskell or something. So you cannot compile one of those languages because, in my opinion, that would be too easy. And there's a lot of constructs that you wouldn't get to write into your compiler, which is important. But yeah, aside from that, as long as it meets the base requirements, then whatever language you want to compile is fine. If you want to create your own programming language, that would be awesome. That's a lot of fun. It's very fun to say, you know what, I want to do this instead of what C did, or blah, 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 blah. So yeah, there's only 2 submission deadlines, the midterm and the final. And again, it's just the compiler, and those are really just progress checks. Well, the midterm is a progress check. If something goes wrong on the midterm, don't worry, you're still in the class, you'll be fine. But just make sure that you are meeting the requirements by the final, and we'll talk about more about the midterm deadline as it approaches. But just try to stay close in line with the lectures, the speed at which the lectures go. And if you have trouble, again, just talk to me and we'll work it out. So we cover a lot of topics. The goal, at least what I'll be presenting, is a C compiler. So we're going to implement a fairly substantial subset of C to a point where you will be able to pass it into either your own compiler or GCC or anything, and it'll compile just fine. So, that's things like if statements, while loops, functions, structs. We're going to do stuff like that. So a total of 75% of the topics that we cover in the lectures is required to get the certification. And out of that 75, 50% are things you have to do, and 25% are things you could do. So I'm giving you some leeway to pick what features you want to add to your compiler, just in case maybe you don't want to write a for loop into your language because you don't need them. This is the schedule. This is outdated. I started writing more lectures and I realized it's a lot of content. So don't worry if this looks compact, because it's getting spread out as I write the rest of the lectures. But this week we're going to talk about scanning, parsing precedence. Next week we'll start doing code generation. And then we're going to get on to cooler things like if statements and variable assignments and stuff like that. You can see in the right column here, we have optional assignments. These are things that I encourage you to do because they are similar to what we talk about in the lectures, but they're different enough that it's kind of just like a little adventure you can go on and learn more about compiler design by implementing these things. And some of them are not in C, and some of them are, like Boolean value printing. That's not in C. You can't print out true because there's no true in C. It's just ones and zeros. While else loops, those are kind of funky. Python has them. Those are fun. N-base integer literals, those are like my favorite thing that I added to Purple, and we'll talk about those when we get to it. But again, completely optional. These would count for that 25% of things you can pick to complete. And so everything we just talked about and more is available via the syllabus, which is linked in the Discord and on my website. Let me just real quick show you the website. All of our lectures and lecture videos are going to go here, charles.systems/PCD. Syllabus is there, the project base is there. If you like my slide design, all of my LaTeX sources are there. We talked about this. One of my core things is that most of the lectures are going to be learning how to convert high-level structures like function calls or while loops into first an abstract syntax tree, and then from an abstract syntax tree into LLVM, which is a pseudo-assembly language. We're going to learn how to apply simple optimizations to our abstract syntax trees. I say simple because we really don't need to learn how to do this, because we pass our compiled LLVM into Clang anyways, and Clang is a way better optimizer than any of us individually will ever be. So we're just going to go over some simple optimizations, but really it's not going to increase the speed of the compiled binary, because Clang is going to do that for us. Unless we compile it without optimizations on the Clang side, which we could. And then every once in a while I'm going to bring up something that we do in the compiler that's different from GCC or Clang or some other big popular compiler. And we'll talk about why we did the different things and whatnot. But so let's start out with actual material. So the first thing is that I want you to spend this week and a bit of next week thinking about what language you want to compile to, what language you want to compile. So if you want to write a C compiler, or you want to write a Python compiler, which you could, I don't recommend it. Pick something with brackets, it's way easier. And then what language you want to write the compiler in. I will be doing a C compiler written in Python because C is really easy to compile in terms of imperative languages, and Python is really easy to write. Funny side note, Python is not easy to write for compilers, so just make sure you're looking at the project base frequently. I wrote this before much of the compiler was done, so I learned the hard way that Python's not great at writing compilers. Who would have thought? If you're brave, I strongly suggest you write the compiler in C, because you can do this really cool thing at the end of the semester called the triple test, where you can see how accurate your compiled binaries are to a fresh GCC binary. So that's like a super cool thing. I'll talk about it later. Next thing is get the project base. It's at this URL. It's also on the homepage for the course. Again, please be familiar with Git. I will show you a little bit about it. So this is it. I'm doing each lecture as a branch because that has this really nice feature where you can compare branches to each other, and you can see the exact list of every single change I made to the compiler since the last lecture. And that's how I started building my compiler, was I was looking at diff notes, so that's very helpful. We're going to go over installation at the end of this lecture. I'm going to help all of y'all install because there's been some issues on the Discord. So if you're running Linux or Mac, and I strongly suggest that you do this on a Linux machine, or the Windows subsystem for Linux, or as a last resort, the UTD CS1 server. I suggest you do that because that's just kind of how the compiler is designed. It's designed around a few Linux features and tools, and also I don't know how Clang works on Windows, so that might be rough. And when you're using it on Linux, all you need is Poetry, which is a Python package management system. If you're using Windows, I provided a Docker file, which works on Linux. Again, I don't have a Windows machine, so I don't know if it works on Windows. But if it doesn't work, talk to me. We'll work something out. Again, the WSL should be fine. So if you're running any modern Windows, I don't think you should have any issues. And if you're asking, why do we have a project base? I thought we were writing everything from scratch. The project base provides some utilities that I didn't want you to have to worry about, like fancy logging and error printing. That's nice to have. Special errors that you can throw, and just like the relative structure of the compiler that really is not as important as the contents of the compiler themselves. So that's why I provided it. Even if you do, if you don't want to do the project base, again, you don't have to. Just make sure that whatever you're doing is mainstream, and it'll be fine. So let's talk about some compiler architectures. And if anyone has any questions, just raise their hand and stop me. I'll be good. So very generally, oh, question?
Someone on Discord said the stream is only showing OBS.
No. Oh my gosh. Okay. Let's see. What did that do? Okay, I'll just, there we go. Okay, that should be fine. Sorry about that. But so very generally, a compiler is a program that takes in as input a program in what we call the source language. And for Echo, that would be C as our source language. And then it translates that program to a new output program in the target language, which in our case with Echo is LLVM. And then it reports errors as it goes. So most compilers explicitly follow something that we call the analysis synthesis model of compilation. If you want to get into compiler theory, it's really cool, but you don't really need to know it at all, honestly. I have a couple books in the syllabus that, if you really like this, you would like reading. And so one thing about Echo is that ours is kind of muddy the distinctions between the different tiers of the model. It's not super important that it does that or it doesn't do that, but this is just a general framework. So the first step that a compiler will go through is called lexical analysis. So it's going to scan a source program into what we call tokens. And if you're familiar with NLP, yes, it's the same kind of tokens. Compiler theory and scanning and parsing, it's very, very intertwined with natural language processing. So that's something cool if you're interested in that. It's going to scan a source program into what we call tokens, and then we're going to throw an error if we encounter a non-token or something, some character sequence that shouldn't be allowed. After that, we are going to take our tokens and we're going to do a semantic analysis of them. What that means is we're going to ensure that the tokens that we've taken in follow the the syntax rules of the source language that we've defined. So we want to make sure that we want to make sure that our if statements have a parenthesis after them and that there's a condition inside, and we don't want to do an if statement with a struct definition inside of the condition. That would be an error thrown in semantic analysis probably, because that's not allowed.
So it's lexically correct but not semantically correct?
Correct, yeah. So, and then after that, we take our tokens that we have assured are correct and in the right order and whatnot, and then we're going to put them into what we call an abstract syntax tree. We're going to talk about more of this the next lecture, but generally an abstract syntax tree is a data structure that encodes the core concepts of the input program, but not every single detail of the input program. That would be a concrete syntax tree, and those are less useful because you get caught up in details when all you really want is the programmer's intentions to be parsed into a tree. And the nice thing about ASTs is that because they are a data structure, a very common one, ours is going to be a ternary tree, we can perform manipulations and optimizations directly on the tree without having to dig through like lists of tokens or something ridiculous like that. And then finally, once we have our AST, we are going to recursively walk through the AST, and we're going to generate code in the target language as we do so. So you could write like a C to Python transpiler. Don't do that. You have to do some kind of assembly language. That's a rule. But in theory, yes, you could just take an AST of a C program and you could spit it out into a Python program, roughly.
What kind of tree do you say this was going to use?
Say again?
What kind of trees did you say this was going to use?
Abstract syntax trees. And again, we're going to cover that more later. I have some resources if the in-class explanation is not sufficient for you. So let's start with scanning. Again, scanning is another word for lexical analysis. That's the first step of our compiler, just reading in a program and converting it to tokens. We are going to start out by parsing simple arithmetic expressions with no operator precedence. So 2 plus 3 times 5, that's an arithmetic sequence expression that we can start out by compiling. It's a nice starting point to go off of because lots and lots of things are expressions. So let's open up Echo and let's see how our compiler runs. So, okay. Project base, echo, and echo.py. So, echo.py is our main script in this project. This main function right here, that's the entry point for whenever you call echo from the terminal. Which Poetry does a very nice job of handling for us. And so it's really simple right now. We can see that we've got some argument parsing. That's also something that the project base provides. Let's not worry about it, but generally the args are going to contain the name of our input program and options and the name of our output program and stuff like that. So in this first line 11, we have with scanner, args program as scanner. So scanner is a class that I've defined that we'll look into in just a second that takes in a file name of an input program stored in args.program like you can see on line 11. Everyone can see this, right? Is it big enough? Okay. Don't worry about the setup tracebacks. It's something hacky that I did because Python's weird. And then we're going to scan a file. So really simple. Initialize a scanner, given a file name, scan the file. Let's take a look at what that actually does. So this is our scanner class for scanning in tokens, like the docstring says. Oh, one little side note, you're gonna see stuff like this. This is called the type annotation in Python. They don't, bigger? At least it's bigger. This is a type annotation. It's basically a way for us to add some compiler checking to our interpreted programming language. Python will let you pass objects in to any function, and it doesn't really do any type checking, which is really annoying for debugging. So I have all these type annotations everywhere, and then I run the code through a linter, which tells me, hey dummy, you passed a list where you're supposed to pass in a string. And then I have to go and fix that, and then some esoteric error that I was not expecting won't happen. So anyways, that's a type annotation. Nothing really special happens here, but let's look at the enter and exit functions. So we had that with as syntax that you saw in echo.py. That's just a little nice Python flavor that lets us kind of initialize and deinitialize an object according to these enter and exit functions. These are special function names. You can't, they mean something specific to the Python interpreter. And so basically it's saying that whenever we open that with as statement, we're going to take in our file name. We're just going to do some checking, make sure it's real. If not, we're going to throw an error. And we're just going to open it. We're going to open it as a read-only file, and we're going to set this little initialize checker to true. Don't worry about that. And then we're going to return this scanner object. And then on exit, so after the with as block terminates, it's just going to handily close our file for us. So just a little making sure we close all our file descriptors. Question?
Why those arguments in exit?
The underscores are placeholders because we don't need those values. I forget what they're supposed to be, but in our case, they're not important. I'm pretty sure they are relevant if an error is thrown in the block, but our program is simple enough that we don't care about that yet. So let's see. Yeah. So back in main, I really wish I had set up OBS right. I have 2 copies of the code running. So we've got this scanner.scan file. That was the one thing that we do inside of this block besides the traceback setup that we don't need to worry about. And let's look at what it actually does. It says it scans a file and it prints out its tokens, the tokens that we scan in from the file. So we can see we've got this self.scan function, which takes in an empty token. We're gonna look into this scan function in a second, and then we print out the token itself. Does exactly what it says it does. Let's look at the scan function. All right, so scan the next token. It takes in an argument called current token, which is just an object that it can scan data into and then share across files. So I call it global. It's a global token. One of the issues I had with Python as the compiler got more complex is sharing global data across files. Notoriously difficult. I don't like it, but I've worked around it. So it's going to raise a syntax error, which that's good. We want to raise a syntax error if we see an unrecognized token. So we've defined our language to be arithmetic expressions. So that's we'll start with integers, and then we have the 4 basic operators: plus, minus, multiplication, division. So if we see like an ampersand or an @ symbol or something like that, that's not a recognized part of our language yet, so we're going to throw a syntax error, obviously. And then it's going to return a true if the token was read, and then a false if the end of file was reached. And that's just going to make sure that this while loop in scan file terminates. So let's look at this function. Let's get into it. We have our base case of checking whether or not the file is empty. If we've scanned in a character, and we'll look into this in just a second. If we've scanned in a character and it's empty, then we've obviously reached the end of the file. So we're going to just return false and close our scanning. Let's look into skip real quick. It's nothing too complicated. Basically, the point of skip is to just read the next character in the file, and then if it's any kind of white space, skip the white space. Because C does not care about your white space. You could write all your C programs on one line with semicolons and whatnot, and it would compile just fine. So we don't care about white space either. Again, if you write a language that does care about white space, this part of your compiler is going to be different. So just keep that in mind. And so it's going to say while this character that we're looking at is a space, just keep on reading it. And then it's eventually going to return a non-white space character. I'm pretty sure there's a bug in that, but we don't worry about those. Scan. Okay, so we've got this possible token type. So let me just pull up the slides one more time. Initialize scanner, enter and exit, back in main. Okay. That's right. So, oh, come on. Okay. We've got this list of possible token types. We'll get into that in a second, but so we've got this character, and it's just a character, one length string, right? And we're going to step through a list of token types that we have defined. So before we get any further, let's look at the token file, because that's important. So I think I've been a little wishy-washy on the definition of a token up to this point. That's on purpose. All a token is just a little data container that stores some information about a tiny little part of the program. And tokens are going to have types. So let me go to this on the stream. Token type. So this is an enum class. Again, more Python flavor. Acts like an enum in your favorite C family language, kind of. But we've just defined some token types. We've got a plus, we've got a minus, we've got a star for multiplication, we've got a slash for division. They all have string values, and that's how we're gonna check whether or not a little substring of our program is one of these tokens. Nothing crazy. And then we've got an integer literal, so that's like 0, 100, 50, something like that. And just for the purposes of being simplistic, these are the natural numbers, so 0 and up, but no negatives, no rational numbers, no fractions or anything like that.
Wait, are they whole numbers or are they natural numbers?
They're natural numbers.
Oh, no zero.
Natural numbers has 0 in it. Okay, that's contentious in the math crowd. I claim that the natural numbers contain 0. Not everyone agrees with that, but 0 and then the positive whole numbers. There we go. That's something everyone can agree on. And then we've got this token class. Again, just stores some data. We're going to store a token type, and then we're going to store a value. So that value is going to hold our integer constant values. So if you have 5 plus 5 as your input program, you're going to have an integer literal token that contains the value 5. Then you're going to have a plus token that has no value because it's just an operator. And then you're going to have another 5 token that has type, integer, literal, and then a value of 5. And I've cooked up this fancy representation function down here just to print it out nice, and we'll see some output of that in a bit. For now, let's go back to the scan function. So we're going to step through every token type. So that was our operators and then our integer literals. If the string value of the token type and its first character is equal to C, we are going to append this token type to a list of possible types that this character could be a part of. This is not important now because our language is so simple, but in the future, for example, if you want to call your function definition keyword func or something like that, but you also have a for loop, or if you have a lot of keywords and they share the first letters of their names, then this optimization is going to help you kind of just check through all your token types faster. Again, it doesn't really matter because we have really tiny programs, but in the future it's going to matter. If we see that the length of this list of possible types is empty, we know that it's going to be an integer literal, because consider the plus, minus, star, slash. Those are all length 1 strings, and so they're going to match a star, slash, plus, minus, whatever. So in that possible token types right now, for an operator, you're going to see a length 1 list containing exactly the token type that we have. But if we're reading a number, none of those match up with integer digits, so you're not going to have a list of token types, you're going to have an empty list. And in that case, we're just going to check, is this character a digit? Because if it's a letter, we don't support those yet, but we will in the future. If it's a digit, then we're going to assign the integer literal type to our current token, and then we're going to scan this integer literal into the token value. So if you have an integer literal 1, 2, 3, this function is going to scan that until it gets to white space or an operator or something. There's some implementation details I'm not going to cover, but you can look at this code after the lecture, and you'll all be starting out with this code anyways, or most of you, so not a big deal. And then if it's not a digit, then we've obviously seen an unrecognized token, so let's throw a syntax error and tell the programmer what they shouldn't have put in there. That's a F string. Is anyone not familiar with those in Python? It's like a format. It's like a way to just put data into a string without dealing with string.format or anything like that. Just more Python flavor. Oh, yeah, I should mention, I picked Python because it's easy to read and write. So if you're not familiar with Python, maybe read up a little bit, but the goal is, I picked Python because honestly, out of the imperative languages, it's probably like up there in readability, right? So if our token types list was empty. If it's not empty and the length is 1, then that's easy, right? We only have one possible token type this token could be. So let's take it, let's store it into the current token type, and then let's return true because we successfully scanned in a token. Otherwise, right now, we're just going to pass. Pass in Python means don't do anything. Eventually, we are going to do things there, but not right now. And that is it. That is basically the entire state of our compiler right now, is we just scan strings into tokens, put them into a list, and then print them out. So let's see that in action. Actually, I might just have a screenshot on the slides. I don't. So let me do that. And I'll do it on this screen too. So let me go to desktop, echo. Go to the project base branch. Okay, and then we've got the scripts file that contains a bunch of instructions for formatting your code, linting it, running it, and then it's got some Docker instructions in there too. Give me 1 second while I do this on the screen. Git branch. Okay. And we will call scripts run, which is going to do all the poetry stuff for us. We don't have to worry about it. And I've got this list of examples, and we've got an example that passes and prints out the tokens, and we have an example that fails. So let's look at pass. So scripts, scan test, pass. So right here, this should be pretty straightforward. We've got all these tokens that we read in from a program, and I'll print out the program that we read in for you so you can see.
What's the 5?
What's that?
What's the 5 after integer literal?
After integer literal, that's the index of the enum. So don't worry about that. But that's just for debugging. So this is the program that we took in. 222 plus 3 times 5 minus 8 divided by 3. One thing to note, we're going to start off with integer division. Do we all know what that is? No? Okay. Easy example. Okay, that's not integer division, that's float division. That's integer division. I'll do that on stream. Python 8/3. That's float division. That's integer division. So this is our list of tokens. We see an integer literal token for 222. We see a plus token for plus. We see an integer literal token for 3, and so on. And so this is what the state of our compiler is right now after we wrote all that scanning code. It's pretty simple right now, I understand. For the next lecture, we're going to write a little interpreter that's going to parse these tokens into our AST, and then it's going to compute the values of these little expressions. So that's fun. Look forward to that. And then next Monday we'll be compiling these to LLVM. So that's the lecture for today. I've allotted the remaining amount of time to helping y'all set up Echo because there is a fair amount of confusion in the Discord. So I'm going to end the stream. Is there any questions? Can't see the slides. Is Lex and Yak relevant in this day and age for compiler design as new tools are available? Opinion on this, please. So I very briefly used Flex and Bison, which are newer versions of Lex and Yak. And in my opinion, they are hard to use. I would say a better tool would be Antler. But I must say, you can't use Antler, you can't use Lex or Bison, you can't use Flex or Yak or anything like that, because that's writing the compiler for you. So we want to write the compiler ourselves. But yes, in general, I would say don't use Lex and Yak. At the very minimum, use Flex and Bison. Look up those tools if any of you guys don't know what they mean. I'm seeing blank stares. But yeah, so that's the one question I have there. So I'm going to end the stream. Boop.